catches you. Okay, hello, welcome everyone, and hello. I'm happy to have you here and to start the lecture, the fourth lecture on density functional theory and application. And tonight we are gonna start with a lecture about um, a specific functional. We are getting into GGAs, and this whole lecture started like follows one storyline that begins with the understanding that chemistry is basically just quantum mechanics, but the equations it leads to are too hard to be solved, right? And in the next steps are the Holmberg-Kohn theorem and Kohn-Sham theory, which we discussed in the last lecture, which basically state that we really don't need the complex monster of the wave function, but we can describe molecules solely based on their electron density. So the Holmberg-Kohn theorem introduces this one-to-one mapping between the wave function and the density. The Kohn-Sham approach is more of a technical solution that tells us how we can compute and optimize the density on a computer with a little numerical trick, which kind of again involves an artificial wave function. And today we are taking a look at how we can improve these very basic concepts, which were still cast in this local density approximation, by refining it to the gradient, to the generalized gradient approximation. We are going to look at functionals because this is really the point where functionals become important. What are functionals? And look at two promising or prominent implementations of an exchange functional, the Becke 88 exchange functional, and the Liang-Par correlation functional. And in the next lectures, we will continue towards hybrid functionals. So this is a mixing between Hartree-Fock and density functional theory, which is often regarded as a major milestone or breakthrough of DFT, because at this point it really became obviously more accurate than wave function theory and very useful. After that, we are going to look at exchange, at a correlation effect, a long-range correlation, which is missing in most classical or purely DFT functionals. It's a very important force if you go to big systems. This is why it was missed for a long time, because people limited by their computational resources were looking at rather small systems in the early days. We're going to talk about range separation, about double hybrids, and a lot more. I don't want to talk about all of this in detail right here and right now. Just a kind of main storyline in the middle here. Okay. And this is a more classic overview of the lecture. We have this Discord server, which Brock set up for us. So just scan the QR code. You will end up there. There's some nice discussions on density functional theory. If you have questions about papers, we are happy to discuss those there. But today we'll start with a short recap indicated by these shaded arrows of the historical and kind of physical context. I'll briefly touch Hartree-Fock theory and how it relates to DFT because of its great relevance. We'll quickly take a look back at the Holmberg-Kohn theorem and the Kohn-Sham approach. Then we're going to move into the basics, like what is a functional, what does this word mean, and how the generalized gradient approximation comes about. And then we take a deep dive into the Becke 88 paper and the LYP paper, how they really work and what they do different or on top of the LDA to improve the chemistry. And the last part of the lecture will be about the performance of these. So we're really going to take a look at the results on the GMTKN55 database from Grimmer and see some surprising trends in the performance, I would say, and how we can rationalize them with what we learned about these functionals. on the in the theory part before. So let's begin with a recap. So the challenge was to solve chemistry via computation. And already in 1929, there's this famous quote from Dirac, which states that the underlying laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. So, right, so we know all the equations, but unfortunately we can't solve them at the time because computers were limited. But even today, we cannot solve the exact equations. But back then, he already noticed that what we really need are good approximations, and this kind of very nicely motivates density functional theory. And this is why I like to start with this historical quote, right? So if you look at the equation that he was having in mind with this quote is the Schrödinger equation, which came about 1925, and you write it down for a molecular system. It has this electronic. Can you see my mouse? I
Yes,
guess
very
so.
slowly.
So here you have this electronic part, which is the kinetic energy, electron-electron interaction, electron-nuclear interaction. You have a nuclear part, which we usually kind of frame, don't think about too much. We just assume it to be constant in the Born-Oppenheimer approximation because we know that electrons are so much lighter and react much faster to any perturbation than nuclei. And then we have these electron-nuclei mixed terms, which is this electronuclear attraction, right? So if you look at these terms, you have many different terms and coordinates for each electron. You have three space coordinates and a spin coordinate. So you have for benzene already a huge many-body problem which you cannot solve. And not even today, it's possible to solve this analytically. You may be able to solve it numerically for benzene nowadays, but this is kind of really what we're talking about. And benzene is not a chemically relevant molecule today. So the state of the art or the method to solve approximatively these equations is Hartree-Fock theory. And just a quick recap again. So what Hartree-Fock theory is kind of the numerical implementation of the linear combination of atomic orbitals approach. You start with an atomic basis functions, you put Gaussians at every atom, you orthonormalize this basis, then you guess some kind of population for these atomic orbitals, which are now molecular orbitals because you kind of orthogonalize them, and you compute how this current density would interact with itself. This will lead you to a new density. This C is basically the C vector gives you the density matrix, which is the density and an energy, and you repeat this process until you get self-consistency. That means until the change between these iterations is not any larger. This is an iterative procedure. It's called a self-consistent field procedure. This is used in Hartree-Fock and DFT, but there's one important major difference, right? And this difference comes from a certain property of Hartree-Fock theory. And if you want to know what kind of the bottleneck of Hartree-Fock theory is, then what limits the size of the systems you can compute, then it's the construction of this Fock operator, which you need for this diagonalization. And this has a core part, which collects all the one electron terms, so nuclear electron interaction, kinetic energy contributions, and here the electron-electron interaction. And this electron-electron interaction has n to the power of 2 Fock matrix elements. So this Fock matrix has n to the power of 2 elements, and in each of these elements, you have the interaction of each electron with each other electron, which gives you another n to the power of 2 integrals for each matrix element. And that means you have n to the power of 2 times n to the power of 2 10 to the power of 4 scaling. So this makes this quite important if you just implement it directly. Another thing which we learned from Hartree-Fock theory, or which we took from Hartree-Fock theory, and which is important throughout the whole of computational chemistry, is the definition of correlation energy. So there's a definition of the word of correlation, which means one electron here moves, one electron here feels that and moves accordingly, but this is not the definition of electron correlation or not correlated motion. It's a more specific definition in computational chemistry. And this definition is that correlation energy is the difference between the complete numerically accurate full CI solution of our system and the Hartree-Fock energy. And the difference between full CI and Hartree-Fock is that Hartree-Fock is the best solution you can get with one determinant. And you use the Slater determinant as the wave function. This is this antisymmetrized product of each electron in each orbital. And using just one determinant is what's called a mean field approximation. What that does is, in the end, if you look at the equations and interpret them, you can understand this as you don't treat each electron's explicit interaction with each other electron, but you only let an electron feel the average potential of the other electrons. This is where the name mean field comes from. So one electron feels the mean field of all the other electrons, including itself, which is also a funny coincidence from the equations. And if you write down this Fock operator, you can separate it in two physically interpretable contributions. One of these contributions is this Coulomb integral here, the Coulomb operator, which in this Coulomb operator then creates the Coulomb integral if you multiply it with the other electrons. And if you look at this here, you have the wave function, the electron 2 in this wave function J, and times the electron 2 in this wave function J. So this is just a complex conjugate. And what this means is you have the same wave function here. So this is a density. And this gives you a probability to find an electron at a certain place. So it's a typical classical Coulomb interaction between electrons. You put another density here, and you have the Coulomb interaction. The other integral, you have also electron 2, but you have the eigenfunction J here and the eigenfunction with another index here. So this is not the same orbital. And what this means, this is a more complex effect because these might not be at the same center. And so here you have a non-local effect because on the other side you then have IJ. And this is a non-classical effect. There's no physical analog in the non-quantum world for this. And what it does technically in Hartree-Fock is it gets rid of one specific case. That is if this electron 2 here is the same as the electron on this side, it feels a Coulomb interaction with itself because it's the mean field, right? But in this case, the exchange integral becomes identical to the Coulomb integral, and the two cancel out. So this exchange integral, which is from the derivation, a result of the antisymmetry of the wave function, corrects for an effect, which is self-interaction, Hartree-Fock theory. It deletes it, and if you change these integrals in some way, for example, approximate the exchange in a way that does not come from Hartree-Fock like you do in DFT, then you don't get this cancellation. That means you can get this self-interaction. And another consequence of this is non-local, this is local. That means you can see this density. You don't need to use two integrals here. You can project these two onto an auxiliary basis function, and then you only have three indexes left here. So you go from 4 to 3 indexes. That reduces the scaling. So you go from n to the power of 4 to k, the size of this auxiliary basis, times n to the power of 2. And this significantly accelerates the calculations if you go to larger systems. In Hartree-Fock, this doesn't help you too much because this exchange becomes the bottleneck. But in density functional theory, we also try to capture this exchange as a local effect, for example, in the local density approximation or in the GGA, as I will show you later today. This is kind of the motivation of DFT. So you could also motivate DFT by looking at Hartree-Fock this way, right? So it's just a more efficient approximation. But it also has some disadvantages. Yeah, so let's go back to this time perspective. We started in 29, and it took quite a while before DFT arrived. So here in the 60s, people actually did the first, 30 years later, people did the first approximate calculations for benzene. There were some basic correlation methods, but everything was quite simple. 1964, the Homberg-Kohn theorems are published, which established this mapping between the wave function and the density, the variational principle. 1965, the Kohn-Sham method appears, and with this, the first real DFT calculations show up, right? Quick recap at the Homberg-Kohn theorem. So we kind of basic idea, you want to model molecules, which in the physicist language, we saw this often in the papers, are the inhomogeneous electron gas by the density instead of the wave function because it's less complex object. Then you need two things. You need the foundation, so proof that there is a mapping between the two, that either of them works basically, and you need to pass to that goal. And that pass, as we just saw from Hartree-Fock theory, is you need some way to know when you are at a very good solution or an accurate solution, which comes from the variation principle, which tells you the better your solution is, the lower its energy. Right? And we took a look at these equations, how it's derived by this inequality. So they prove by reductio ad absurdum that the same density cannot emerge from two different wave functions. I don't want to go into detail. I feel like I already go quite a bit too detailed in this review, but I think the lecture is on YouTube if you want to see it. The next thing you need, besides the foundation and the path to the goal, is a protocol that you can implement on a computer. And this comes from the Kohn-Sham approach because it's not so easy to systematically manipulate the density. And the Kohn-Sham approach starts by reintroducing a wave function. But it's not a wave function which with the intent to accurately capture the system, but the intent of the wave function in Kohn-Sham theory is just to produce the exact same density that you get for a real system. Now, you could think this is a conflict with the Homberg-Kohn theorem, because as we just learned that this same two wave functions cannot produce the same density. But in this case, this is not a problem because we have an artificial wave function. And the external potential, that is the position of the nuclei, is identical. So in this case of the Kohn-Sham approach, they postulate that this is not a many determinant wave function like we would get in full CI for the exact solution, but that this is a single theta determinant. So within the mean field approach, like in Hartree-Fock, we use this Hartree Coulomb interaction. Hartree term, this is the Coulomb interaction, plus some, they call it magical functional, or I call it magical functional. I'm sure they didn't call it this way. But what this magical exchange correlation functional does is it captures everything that is missing from the Coulomb interaction in molecules. So you have this energy split up in the kinetic energy in the nuclear electron interaction. This is this one electron interaction still. The electron interaction in this Coulomb term. So this is just a Coulomb integral from Hartree Fock. It's exactly the same integral. But then we have an exchange correlation functional or potential, which captures everything else. This should capture the exchange, which we just saw, but in a slightly different way as in Hartree Fock, and also correlation effects. So the difference to the full CI. And this is not something which they know. They just say, let's assume this exists and we can work with this. And
Can I ask
if
a
this,
question?
yeah, sure.
So, if I would leave out the correlation part of my functional,
Yes.
run a calculation and compare it to Hartree Fock,
Mm-hmm.
would that give me the extent of the self-interaction error then for that specific exchange functional? Because if Coulomb is the same, the
Coulomb is the
Coulombic
same, but
terms
the exchange is not the same, right?
exactly, and because the exchange is not the same, is it not the same because it's intrinsically not the same, or the difference
Yes.
is actually the self-interaction error?
It's not the same because exchange it's also called exchange, but Hartree-Fock exchange is a very specific way of exchange. You don't have that type of exchange in density functional theory. You try to get the exchange from the density with something that in the end also looks more like a one electron operator than um, a non-local exchange integral.
Okay, so there's
So,
really
and you can do DFT calculations without correlation. Correlation is the smallest part. I think it's coming on one of the next few slides. So it's not that big of an issue, but it will mess up energies, chemical energies that come from the calculation because
sure it
of,
will, but it will do so more than just by the error introduced by self-interaction. It will
yes,
mess it up because the whole thing relies on the fact that you also include correlation in the end. It's not
the
something
whole,
that
yeah.
that DFT adds on top of Hartree-Fock. It does it as well, but
Mhm.
it relies on it to for the
Um,
whole thing to make sense.
yes, but also you can use Hartree-Fock to calculate chemical energies, right? And if you do
Sure.
this, you
Yeah.
have one fundamental problem, and because people were for a long time limited with to that, what they did is they came up with recasting chemical reactions in a way where the amount of bonds is the same between the product and the educt side. Because you have a huge systematic error if bonds are if electrons are in a bond or not. So if you change the number of bonds, you lack error compensation. And then
Hmm.
Hartree-Fock
Hmm.
and chemical energies are useless. But if you keep the number of of bonds constant, then you have error cancellation, and then Hartree-Fock chemical energies can be okay-ish, right? Then you can get
Yeah,
at
yeah.
least an idea of them. But this is really maybe in two or three slides when I have this overview, you will understand it in a better way. Okay?
Okay. Yeah. Thanks.
So, but thank you for the question. Because of this magical correlation function, now we have a non-interacting model, so kind of a single determinant wave function which produces the exact density as the real system, and we get, at least in theory, an exact result. And the problem is that nobody knows how this magical function looks. It's just they just prove that it exists, kind of. So what this does, if you think about the relation between like the Hamiltonian wave function theory, the density and the density, then you can sort like in this triangle where DFT is the direct connection between the density and the Hamiltonian. This is the Holm-Backward theorem, right? It states that there is this direct connection, and you don't need to go via this complex construct of the wave function. But what Kohn-Sham theory now does basically is it takes the Hamiltonian around the wave function, the Kohn-Sham wave function, not the real one, this non-exacting artificial thing, to get the density, which then gives us the energy and all the properties. right? So it's a clever construct which makes DFT really useful. There is non-cone sham DFT. It's called orbital-free DFT, but it's not. It not has not nearly the relevance of cone sham DFT, at least in chemical for chemical problems. So while cone sham is similar to to Hartree-Fock, technically the philosophy between the two is really different. And this is a point I always um, uh, point out, or I always focus on, because I think it's very important to understand the difference between the two. Right? In Hartree-Fock, you have an exact path to the lowest energy approximate wave function. And the approximation is in the wave function. In the wave function is that it just one Slater determinant. Right? And this, for example, has the consequence that you don't have any correlation in there. And DFT is an approximate path because we have an approximation in this Hamiltonian in the functional, which we have to approximate because we don't know how the magical functional looks, to a formally exact density. So the approximation Hartree-Fock is in the wave function, the approximation DFT is in the Hamiltonian. And because of this, Hartree-Fock is internally consistent and self-interaction free. Exchange, it's a consequence of the shape of the wave function. It cancels the self-interaction error. It cancels the self-interaction. It's consistent. It's uncorrelated. That means you need post-Hartree-Fock for useful accuracy. So you need some kind of correlation treatment, MP2, to get rid of these bond number inconsistencies we just discussed. And this makes it computationally demanding. Right? Because with every additional determinants, and there are usually thousands or millions, you have an increased computational demand. But it's systematically improvable. So you can just consider all singles, doubles, triples, quadruples, excitations. This is a way to create more determinants. The more, the better. And you can define this CCST gold standard. You know, for most well-behaved systems where you don't have huge multi-reference character, this is usually better than 1 kcal per mole with respect to experimental data. And it's globally variational. CCSD is not, so some post-correlation methods are not, but if you have a specific class of correlation treatments, the energy you get in a certain basis set, you strictly know the lower the energy, the better the wave function is. With DFT, it behaves a bit different. So it's correlated from the beginning because we have this approximate correlation effects in there, which gives it useful accuracy at the STF level, much better than Hartree-Fock, but it's computationally inefficient. It's partially inconsistent because, for example, we have this self-interaction error, but this self-interaction error also mimics correlation. So we get some kind of correlation at a much lower computational effort, or can get it. It's not systematically improvable, and sometimes you have these unexpected failures where DFT just breaks. The result is suddenly, the errors suddenly are unexpectedly large, and you always have to carefully test and benchmark your results. Okay, and with this, I think I'm at the end of the recap. And in the next few slides, we'll take a look at this magical functional. So first, what is a functional? And then with two specific examples. Are there any more questions regarding this first part? If this is not the case, let's continue. So very basic, what are functionals? What does this word mean? Right? You all know what a function is, right? A function assigns a value to an input value. F of x is y. So you project one value onto another value. A scalar onto another scalar. A functional assigns a value to an input function. So you go from the function of x to a certain value. And a density functional is now the same. Oh, now we have a problem with the graphic. Let me restart the presentation. Naturally, this did not happen during testing. Anyhow, so this equation shows an exchange correlation. This is a density functional assigns an exchange correlation energy to the density, which is a function of R, of the three-dimensional space. And this equation reads that I'll open it here, quick fix. So the exchange correlation energy as a function of the density of R, to get this exchange correlation energy, you integrate the product of the density and this exchange correlation construct here. What this is just the exchange correlation potential. And the exchange correlation potential itself depends on the density. This is much like Hartree-Fock, where we have these electrons, we sum up all the electrons, we get the mean field impact or influence of these electrons on each electrons. The same way here, we have the density that creates a potential. The potential interacts with the density itself to give you an energy. Right, then how does it look? Let me see if this next equation looks fine. Wow. So the exchange energy of the unified electron gas, this is something we discussed in the last lecture and the lecture before that. After Slater and Dirac this is just exchange, right? So this is the part which we just discussed. Niels, you have this density, you take cube root of the density and so have some normalization. And this is all you need. You multiply, you plug this into this equation here. You integrate over the product of the density with this, and you get an exchange energy, sorry. So these factors here are kind of empirical. This is not something, this alpha here is empirical. It's not something that is fixed. Kind of depends on the system which works better. But this is a very simple way to get an exchange correlation energy because you just need the value of the density at this point in space. Right? You don't have any non-local contributions. You don't need to worry about orbitals. You just need the density, the value of the density, and not even its gradient. Right? So the exchange energy at the point R in this of an exchange of a density functional depends only on the value of the density at this point. And this is why we call it a local density approximation. And there's nothing else entering this equation as the value of the density itself. And this, in the Homberg-Kohn and Kohn-Sham world, in these initial papers, they just used this unified electron gas, which is a hypothetical electron gas, which has the same density all across space. There's a high density and can have a higher or lower density, but the most important point is that the density is constant. This is not something which you have in molecules, but this is more like the valence electrons in metals behave like that. So this was sort of or conceived as a model for valence electrons in a metal, right? Where the potential of the nuclei is kind of evened out by the shielding of the core electrons, and then you have this valence band and this reduction band, and they feel kind of a reasonably similar potential everywhere in space. You can model it with a unified electron gas. And this works surprisingly well, even for atoms and molecules, although they don't have this property that the density is the same everywhere. For example, the exchange energy is only 10% smaller than with this non-local, much more complicated expression that we just saw in the Fock operator. What about correlation? So this is just an expression for exchange. Correlation is a bit more complex, but correlation is also less important, right? Just a reminder, we had this, I think, in the second lecture. If you look at the total contributions for benzene, it has a total Hartree-Fock, I think it doesn't matter if it's Hartree-Fock or DFT energy of minus 231 Hartree. So this is the energy you get if you pull all the nuclei and all the electrons together from infinite distance. Then the one electron contributions, so the nuclei electron interactions, the kinetic energy of the electrons is about minus 700. So it's off the scale here. The two electron contributions, that means the electron-electron repulsion, is plus 279. And this is the sum of the Coulomb interaction, so the repulsion in green, the exchange interaction 10 times smaller, and this is typical. We go a factor of 10 from the Coulomb energy to the exchange energy, and then you go another factor of 10 from the exchange to correlation energy. And this tiny pinky thing here is the correlation. Right? The consequence of this is, if you take a look, this is minus 3 Hartree, right? 1 Hartree is 27 eV. Chemical energies are more like 0.05 Hartree, or isomers even less than that. Conformers much less than that. That means that this tiny energy here, if you make a systematic error in it, it's hugely important. And now, Niels, you will perhaps agree with me that if you make a systematic error in this, or don't consider that, no chance to get anything useful.
Oh yeah, no,
Chemical.
no question about it. It was just that if the underlying physics or math behind the inclusion of correlation to DFT rather than the lack
Okay,
of,
you
or
were
the
just
description
aiming at
by
this.
mean field in Hartree-Fock. If you go back where you have the simple LDA description and then you go to GGA, or even include the kinetic terms, if you get the mathematically correct description and then take the difference between a DFT calculation, like a perfect one in parentheses,
Mhm.
versus Hartree-Fock.
If you
With,
have the perfect one, then I have to reconsider my answer. I thought you mean like one of these approximate functionals. No, but
no, no,
if
sorry,
you
sorry. I
well,
meant the magic functional that you had on the
mhm.
slide.
That's a good
Or
point. I
if
can't
the
answer.
underlying math sort of says, okay, the description of exchange in DFT, no matter how good your approach is, always necessitates to also include correlation,
Yeah,
because the two are interdependent
they're
for
often
whatever
closely
reason.
related.
Yeah, sure.
There are some functionals, for example, where you can separate exchange and correlation. Perfect. So
Mm, okay.
in the practical functionals we have, it's a different story, but it would be interesting to think about this for the exact functional. It's even a better question than I thought. I should maybe discuss this with an AI.
Let me know.
So because of these two factors of tens, you go from 300 to 35 to 3, and you're still much larger than chemical energies. It's of utmost importance if you want to do computational chemistry that you have consistent results, that you do everything in the same way between the products and the educts if you have a chemical reaction. Because what you actually do is, if you run the numbers, the chemical energy of 1 kcal per mole to the kind of typical Hartree energy of a molecule of 1000 Hartree is the same as the mass of a large container ship compared to its captain. So basically what you do if you measure chemical energy by computing edux and products, you try to determine the mass of this captain by measuring the ship with him and without him. So you need a very good and very consistent scale, right? So if you have any inconsistency in the basis function, if you have any inconsistency in your integration grids, no chance. Right? This is because you have these energies spanning several orders of magnitude. So the last point was this correlation energy. What is the correlation energy in the local density approximation? So the correlation is formally more involved. So it's not as easy as the cube root of the density at this point. What we have to first introduce to look at the equations is this effective one electron radius RS. And this is just a sphere that at a given density integrates to one electron. And then you have two expressions, one for the collation energy in the high density regime. There you have just this evolution depending on the parameters A, B, C, and D. And then have a low density regime where you have a different evolution with the parameters G0, G1, and so on. And these are published, these approximations, I think, are mentioned here, but the parameters came later. So what people did to get them is they just calculated the accurate total energy of this unified electron gas, and then from this value they subtract the Slater-Dirac exchange energy, and then you isolate the correlation energy at a given density. Right? You can calculate its numerical value and then fit a functional to reproduce these values at a given value. Because the only thing, again, that enters, we're talking about the local density approximation here, is the value of the density at this point in space. There's no gradient entering, there's no non-local contributions. It's just the value of the density in space. So clear mapping, one value of the density, one value of the correlation energy. Very, very simple. And people did this, people fitted these parameters. There's different versions or variations. Fosco, Wilk, and Nurser as prominent. You probably know the VVN3, VWN5 versions. PW91 is also another one which is typically used. Their differences are tiny. Usually it doesn't really matter which you use because, again, we are talking about the smallest part in a functional, the smallest contribution. It's more important that you are consistent than what you actually use for these parameters. How well does it perform? So this is my slide representing the GMTKN55. So for everyone who hasn't been to the last lectures, this is a huge database with lots of chemical energies, simple atomization energies, ionization energies, double ionization energies, electron affinities, non-covalent interactions, and distorted structures, barrier heights. So there's kind of a nice average cut through what the typical computational chemist would face during his work. And there's highly accurate reference data, coupled cluster, singles, doubles, perturbative triples, converge to the complete basis set limit. And then we run the same calculations with different functionals, and you get this kind of weighted mean absolute deviation. The best functionals we have nowadays, this is a paper from 2017. Stuff has happened since then. So the best functional nowadays are around 2 for double hybrids. There's some triple hybrids which go as close as 1. So this is then almost at the level of the accuracy as the reference method. The best double hybrids, I think, are now at 2. The best hybrids we have nowadays are 3-ish. So I mean, B97MV is, I think, 3 point something, closer to 3 than to 4. These are range-separated hybrids. Over here we have GGA functionals. Somewhere here is B88 BLIP. This is the one we will discuss in a second. But how does the LDA perform? So if you use Slater exchange, so this very simple exchange, again, it's just square root of cube root of the density integrated with the density. You get the MAD of 17. This is just out of the scale, and this means you're much better than Hartree-Fock. And so this very, very simple. Hartree-Fock doesn't know about densities, but I guess Hartree-Fock, you could say it's more complex than this, and it still works surprisingly well. MP2 sits at 6 kcal per mole, so somewhere in the ballpark of hybrid functionals. And so this is what I mean by it works surprisingly well. So the question that this lecture asks next is, how can we improve on this local density approximation? So what's the main difference between this unified electron gas model and the molecule? And here you see the density, an old picture of the density of a water molecule plotted on 2D. Water, the molecule sits here in the plane, and the Z value kind of gives you the value of the density. And you see that the density is nowhere near constant. You have this huge density here close to oxygen. Oh, Hisakro asked, where does PBE 0 sit in the previous table? So let me quickly go back for a second. Why is it not doing what I want? PBE 0. PBE 0 is somewhere here with the most. Oh, I can't find it. There it is. See it? Right there. So PBE 0 is a little bit worse than MP2. Just one notice, these functionals here, these results are all with the dispersion correction. They are all usually, I think, with D3, with Becke-Johnson damping, right? So this is PBE D3. So the main difference, let's come back to the last slide, is that the density varies, and quite a bit actually, if you move across a molecule. So the most obvious improvement of the LDA is not yet going non-local, but taking into account the value, not only the value of the density, but also the gradient of the density at a certain point, right? This is why this density, the GGAs are sometimes called semi-local functionals, because it's still kind of local because you look at the gradient only at one point, but the gradient at one point contains information from the points around it, right? So semi-local, I don't really like this name, but this is the name that stuck. So be aware that people use it. And you can rationalize this expansion as the second element of a Taylor series, right? If you evolve the exchange correlation potential or energy, then the LDA is the constant first term. The second term depends then on the gradient of the density. The next term would depend on the gradient of the density, so the curvature of the density at this point, and so on. And you can derive this analytically. You get the value for this mu here, but no actual or no practically used GGA functional uses this exact form. There is one, it's called SOGA. It's a density function. It's a density functional approximation. So it's the functional you can use in some codes, but it's not used because it's just bad. Right? So what people actually did, and this is what we will see in a minute, is that people use this idea as a starting point for their considerations, where this u c square and beta are used as parameters. And one very, very famous exchange correlation functional is the B88 functional. It's the Becke exchange functional from 1998. And if you take a look at the paper, this paper has 51,000 citations. It's still being used today, and it's growing. Niels, you have a question?
Yes, sorry, one more.
Sure.
Is there a similarly intuitive explanation for why the second derivative helps with the description? Like it's integrated in the Minnesota and TPSSH or TPSSA as
I mean,
functionals.
many functionals now use it. Um, And mm, I don't know if there's an easy way to explain it. So it provides more information, but it also has adds some problems because to get the curvature right, you need a very fine integration grid. Otherwise, you start to see more numerical noise than you see actual data.
Yeah.
So this you need to be careful how you use this second derivative
Mm.
to help most functionals that started using TPSS, for example, wasn't that much of an improvement over PBE that people stopped using PBE and started using TPSS. And in the
Sure.
same way, these Minnesota functionals, where it was not used, so these Minnesota functionals are kind of a different type of functional. They are not derived from the fundamentals. They just put in different terms where this kinetic energy density is how people call it,
Just
shows up.
makes
And
more
then,
sense. Okay.
and then they fit it into experimental data, and they saw that adding these terms improved the results. But whenever
Hmm.
you add another term to a fit, giving it more flexibility, it improves the results. But this doesn't mean that there's new physics. I think the first real improvement, and this is my opinion, was seen in a fundamental function was seen with scan and R2 scan, especially. And the problem here is if you look at this water density here, right? It's a density of a molecule and it decays to zero at some point. And this is something which you have in molecules, but in a solid or in ice, you don't have that. In ice, you have molecule after molecule after molecule.
Sure.
So you
Yeah.
have kind of a different type of density. And what you see is, if we will discuss this in a minute, that some GGAs, you need a different type of GGA for metal than you need it for a molecule. PBE is good for many molecules, but it's poor at lattice constants, for example. There, PBE sol is much better. PBE sol is a more LEA-like variation of PBE. And there is a reason for that. And that is the singularity of a molecule decaying to zero, which you don't have in a solid. To switch between these two regimes, you can use the kinetic energy density, the second order
Mm,
gradient,
okay.
right? The
So it's
curvature.
really just another tool in the toolbox rather than a rather than a fundamental thing that really makes sense, such
Exactly.
as the
It
GGA.
is a fundamental thing that makes sense, but you have to be careful how you use it. And I think only with Scan in 2019 or so, or 2018, it was really put to a use where which which taught the functional to detect if it's kind of modeling a solid or a molecule,
Mhm.
right?
All right. Thanks.
But you will see, I can much better explain this if we go into the Becke paper and take a look at it, and afterwards you will understand this better. Okay, so let's continue, and then I will come back to that, and please remind me if I forget to come back to that.
Go.
So this paper from Becke is like really a fantastic paper. All his papers are really nice to read, even many years after they have been written. And this is not even some papers that were published yesterday are that nice to read. So let's just read through this. So the current corrected density functional approximations. So this is not the first one. He basically builds and shows a new one. But current density functional approximations for the exchange energies of atoms, atomic and molecular systems fail to reproduce the correct 1 over r asymptotic behavior of the exchange energy density. Here we report a gradient-corrected exchange energy functional with the proper asymptotic limit. Our functional, containing only one parameter, fits the exact Hartree-Fock exchange energies of a wide variety of atomic systems with remarkable accuracy, surpassing the performance of previous functionals containing two parameters or more. So he's kind of addressing your question there a little bit, Niels, because he tests he judges the quality of his approximation by the ability to reproduce the more complicated non-local Hartree-Fock results, right? But before we dive into this paper, I said I want to dedicate this lecture to Becke because very unfortunately he recently passed away end of last year. And usually people tell you which awards he won. He won kind of all the awards. So I put the list there. It's a long list. I don't want to read it, but I want to focus instead on the contributions this single human being made to computational chemistry. And this is really an impressive list if you think about it. This is a lecture about density functional theory. And you see in red on this slide every lecture which is kind of on a topic that he helped or brought up by himself. Right? So first, what we're talking about in a minute is the B88 exchange functional. This is not the only GGA, it's not the first GGA, but it's a cornerstone and it's used to this day in countless DFAs. So 51,000 citations. He has two papers which are in the Nature list of 100 of the 100 most cited papers, and there's just look, it's just him, right? So this is impressive. Besides the functional, he also in the same year invented Becke integration grids, an essential part of DFT, which are all also, if you look in your quantum chemistry program, you will probably find somewhere the statement that a Becke integration grid is used. He helped to conceive, or he also conceived hybrid functionals to rationalize this mixing between Hartree-Fock and DFT, why it's useful for thermochemistry. This will be in the next lecture. And the functional he invented, or one of the prominent functionals based on his work is this B3LYP functional, which is still widely used today, maybe even a little bit too wide. Then with B97 and B98, 10 years after B88, he came up with an idea to fit exchange correlation functionals, which have a flexible form to experimental data. And this paper is the basis of a whole school of functional development, which was picked up by other people. This is the lecture after the next lecture, I think, or the one after that. So we have a lecture on the different schools of functional development, where his paper is the starting point. Then he also came up with a dispersion correction. It's the exchange dipole model. This is not something which is the most prominent, but it's also not something that's bad. So you can still use it today. It was he published in 2005. And finally, for this exchange dispersion exchange dipole model, he came up with a type of damping function. He called it a rational Becke-Johnson damping. And this is the one damping function which is used, for example, by all the modern D3, D4, the upcoming D5 dispersion correction, which we will talk about in the next lecture. So it's really, you cannot overstate how much this single human being shaped the field of computational chemistry. It's very impressive, and yeah, it was very sad to hear that he passed away, unfortunately. Okay, and with this kind of sad part, let's continue honoring him by taking a look at yeah, this impressive work of his. So I will just, because it's so nicely written, read through this. I cannot cast it in better words. It is well known that the Hartree-Fock exchange energy of an inhomogeneous many electron system can be reasonably approximated by the so-called local density approximation, right? This is what we just discussed, which in atomic units is given by this expression. It's the cube root, which we discussed before. He just multiplied it with the density, so you then have rho times rho to the power of 1/3 becomes 4/3. Where sigma denotes either up or down electronic spin, where the integrand is essentially the volume exchange energy density of the uniform spin polarized electron gas of the spin density rho sigma. But the LDA typically underestimates the exchange energies of atomic and molecular systems by roughly 10%, and corrections for the obvious non-uniformity of atomic and molecular densities have a long history. This is what I just showed you, the non-uniformity of the density in the water molecule. Corrections depending on local density gradients have been derived by Sham, among others, and also have been proposed in a purely empirical context. See, the empiricism is already moving into density functional theory by Hermann, Van Dyck, and Ortenburger. Non-local corrections of other types, such as the weighted density scheme of Gunnarsson and Jones, have also been reported, but gradient type corrections have received most attention due to their great simplicity. The lowest order gradient correction, LGC, to local density approximation is uniquely determined by dimensional analysis and is given by, this is the term which I just showed to you, where beta is a constant. But this LGC functional, named X alpha beta by Hermann, has, however, well-known and severe deficiencies. First of all the corresponding exchange potential diverges asymptotically in atomic and molecular systems and thus requires ad hoc adjustment in practical applications. So why is that? And there's maybe a reason for this, and we can connect this to this Taylor series expansion. Right? Because if you cut the Taylor series after a certain element, the divergence can emerge because you're missing the higher order terms. Right? This is like MP2, which we know does not necessarily converge. MP3 is not necessarily better than MP2. Right? So if you cut a series after the second term, things like that can happen. And the right thing would be to include the next level, next order term, but this is sometimes not possible. So if you want to stay with the second order, you need some way of making this more practical, right? So this LGC is impractical, and moreover, the value of this constant, beta, is unclear from the derivation. And motivated by the first of these problems, we have introduced the following modified gradient-corrected exchange energy functional on semi-empirical grounds. And so he took a look at the equations and recast them in a form which does no longer have this divergence issue. Modify and generalize, therefore generalized gradient approximation. And one thing which you see in this, you get it right. So this just continues here. I put it here, and here now he introduces this quantity here, and this is the so-called reduced density gradient. This is central to many GGAs and often abbreviated with just an S. And what this is the relation between the value of the density and the gradient of the density. So it combines these two quantities into one, and most of the exchange correlation potentials depend on this quotient. This X alpha beta gamma functional in Ref 5 is determined by the reasonable criteria that dimensional consistency is satisfied. The LGC function is obtained in the case of small density gradients. So if this becomes small, that means we go to the LDA limit, just a constant density. This comes back to the LDA, the LGC, and the large limit corresponds to the asymptotic exponential tail of an atomic or molecular charge distribution. So if you have an atom, this is what we just discussed before, or a molecule where the charge decays to zero, at some point, this denominator becomes very small, so this thing becomes very large. Right? Because you still have some curvature, but the value of the density becomes at some point very small. The function of equation 3 is certainly not the only conceivable such function, but is probably the simplest. If parameters beta and gamma are chosen on the basis of a least squares fit to a selected atomic data, so there's already some fitting, you see, we find that the semi-empirical functional, this is what he calls this guy, approximates a wide range of atomic Hartree-Fock exchange energies extremely well. So let's look at the table from the paper. This is the exact result. Exact here means non-local Hartree-Fock exchange. These are the atomic systems. This is what the LDA would get you. And this is what the present work. So the Purdue Wang exchange, this is present work, would get you. And you can compare these numbers, but for your convenience, I plotted them. So if you look at the numbers like this, it looks like, well, 88 is quite fine, right? But I use this, I want to use this table for a little excursion into how the visualization of the data can be decisive for the conclusion. So if you say, well, we should look at the differences here because, right, we have very small values here, very high values there. So let's just plot the differences. And if you look at differences, then you think, well, the LDA works quite well for helium, but very poorly for radon. Can anybody has an idea for the why that could be? I mean, helium is just a little blob of 2 electrons, right? But in radon, you have this huge increase towards nucleus, lots of electrons, huge gradients. So this is kind of the least LDA-like, least UEG-like system. But if you now look at the, not of the absolute error, but at the relative error, you see that actually our interpretation and the rationalization of it was nonsense because the relative accuracy of the LDA is worst for helium and best for radon. And there you see how, in all of these, you see how actually very good already this first semi-empirical refinement of the LGC here works. Right? 3 plots, 3 different interpretations. If you look at some data like this, always at least look at relative and at absolute errors. And think about which ones are more important, or maybe if you should consider both. So however, there's still a problem, right? The exact asymptotic behavior of the exchange energy density of a finite many electron system, so molecules or atoms, not a periodic system, is given by this expression. It should behave like minus 1 over r, where this is the Coulomb potential of the exchange charge or Fermi hole at a reference point r. And this is related to the total exchange energy. So what is he talking about? What is a Fermi hole on exchange charge? Well, these are important concepts which you will find. So I thought I put here these 2 animations which show you what these concepts are. So the exchange, the Fermi hole, or sometimes exchange hole, is the interaction of one electron with the mean cloud of other electrons in a molecule. And this obviously depends on the spin of the electrons. And here on the left, you see the helium density of a helium atom, where the conditional 2 electron density of a helium atom. So this is not a single electron density, this is 2 electron density, where one of the electrons is indicated by the position of the stick. It's moving around. You see that in this case, in the singlet case, the second electron, the other electron, is moving along with it. See, this is the p orbital of the helium atom, and you see how the density follows because the spin is the same, is different. So these electrons can pair up and follow each other. The complete opposite is the case for the triplet state. Because 2 same spin electrons can never be in the same spot, you see that there's a maximum on the opposite side of this. Right? And this electron, you can think about this as if this electron carries a hole with it around, right? Because there's kind of a hole where there's a lack of electron density right around this by other electrons of the same spin. In this case, you have a hill which this is carrying around. with itself. Now, if you don't have a helium electron, which is very specific, but a large molecule, or even the metal in a unified electron gas, then each electron kind of carries around with it a hole around it where other electrons' probability of being is reduced. And this is the so-called exchange hole. And it's just a concept which you will often encounter in papers discussing these things. So I thought I show you this nice visualization. So what does this mean? So this result reflects the fact that for every for reference points very far from the finite system, the Fermi hole remains attached to the system. Now imagine the case that you take this guy far away from the molecule. And you have a local exchange functional. Because it's local, this electron, this density, cannot know about the electron that's far away from it. And this is a problem. This non-locality starts to become, and you can construct situations where this really leads to issues. For example, issues like the self-interaction error. And now the question is how, despite this local character of the approximation, how can we keep this behavior or avoid this problem from breaking our approximation, right? So given that also the Fermi hole contains exactly one electron, equation 5 is obvious. A very recent discussion of this problem has been provided by March. Furthermore, the asymptotic behavior of the spin density is also known and given by this exponential function, where alpha, where R sigma is a constant related to the ionization potential of the system. In view of this known asymptotic density dependence, we propose a new gradient-corrected exchange energy functional that reproduces the exact asymptotic behaviors of equations 5 and 6. So now he comes and further, in the second step, refines his first refinement further to fulfill certain constraints. So this is a kind of a plot of these equations. So this is equation 8, the final form, the B88 form. Then we have equation 3. That was this guy. This was the first refinement, which removed this divergence. And then the original equation was this equation 2 here, right? This was the original Sogger, basically. And if you plot them, now we have this enhancement factor, this reduced density gradient. Remember, this is the ratio between the gradient and the density value. And the further this becomes, the bigger this becomes, the further we are away from the unified electron gas. And this becomes bigger if you go away from molecules, right? If you go away from a molecule into the distance, into the vacuum. This original equation diverges. This is what you just described, right? It goes to infinity. Then this equation 3 saturates, and the saturation is a problem. This is the problem we just discussed with this exchange correlation hole, and his final form has this behavior where it continues to rise here. This is the Becke 88 GJ functional, right? It has the LDA in there, LDA exchange minus this correction factor. So what did we see there? He generalized this analytical expression. The formally correct Taylor series expansion just served as the starting point. Then he makes these equations, he adapts these equations to be numerically stable, not have a divergence, satisfy known asymptotics and requirements. We know how this should behave, assuming these model densities. We know how the density should behave when you go away from a molecule. He puts this in there. This is the second refinement. And then he takes these parameters, this beta, which was unknown, and fits it such that it reproduces Hartree-Fock exchange energies of rare gas atoms, so very simple atomic systems. So in this, in something else we saw is that this reduced dimensionless reduced gradient is the key quantity. So Becke calls this X sigma, usually it's called just S, and it enters this so-called enhancement factor. And enhancement factor was the y-axis in my plot. This is how much we add or subtract from the LDA exchange. And depending on the focus or requirements, and this comes back to the discussion we had before with Niels, DGAs differ in their enhancement factor. Now, this is a typical evolution of this S for a nitrogen molecule. And here you see what I mean. So you have the one nitrogen atom sitting here, the other one here. You have a factor of close to 0 in the middle. This is where kind of the minimum of the density is. There's no gradient, right? Because we have a minimum. This is a bond critical point. If you like the NBO analysis, you have two maxima. This is where you have the inflection point of the density, and then it approaches the maximum. The maximum, there's another minimum, right? And then we go back on the other hand, and then we go out to infinity here, and you see how this reduced density gradients increases again because the density value becomes very small, right? Is this all clear? Very important that this is understood. And now, as a function of this S, this enhancement factor tells you how much the description differs from the LDA. So how much lower or higher the exchange energy is. You remember that the LDA underestimates exchange energies by about 10%. So we increase the exchange energy depending on this enhancement factor. And this enhancement factor looks quite similar at first glance for PBE and B88. Here's a couple of more functionals. Now we go not from 0 to 2, but from 0 to 6. Some of these functionals you might know, for example, ref PBE. It's like a refinement of PBE. It has quite a large, high enhancement factor here, but it starts to level off, whereas B88 just continues rising here, right? You see that prominent functionals like PBE mostly follow this saturation curve, where B88 keeps rising, PW86 keeps rising. Some of the functionals here, PW91, levels off at some point, right? PBE Sol, something I just mentioned before, is very low in the enhancement factor, and what this means is it's very close to the local density approximation. So now, this is all very good and fine, but what does this mean for the performance of the functional? I would love to show you these results now, but I think before we move to the performance of the functional, there's one thing missing. We have now discussed this exchange functional, but before we can use this functional to apply to the GMTKN55, we also need the correlation functional. And the perhaps most prominent correlation functional that is used in conjunction with B88 is the LYP correlation functional. So let's take a look how the LYP correlation functional works. This was also published in 1988. The Liang-Par correlation functional paper has 93,000 citations. These numbers are from 21. I forgot to update them, so probably they are now hitting 100,000. And this is an interesting one because it differs in character a lot from what Becke did. They basically derived an early, from a time where MP2 was just too costly for everything, approximation for the correlation energy of a Hartree-Fock wave function. And use this approximation to MP2 correlation to construct something which is a correlation functional. The paper, the original paper, is from Colle and Salvetti. The development of the Colle-Salvetti correlation formula into a functional of the electron density. So they took something which was made for wave functions, which is orbital dependent, and made it and recast it into something which depends on the density, on the local density and its gradient. The original, or Brock just wrote that LYP is at 17,000 citations now. Wow. So this is a juicy increase over 5 years. I'd be happy if any of my papers had the difference in citations, man. No, but this number alone is not so interesting. I think what's more interesting, if you can look that up, Brock, that would be great. How much citations does the Colle and Salvetti original paper had? So these are the guys who invented this stuff. And we will take a look at this paper now. So we maintain that this line of research is significant and fires absolute absolute calculations of the correlation energy are extremely laborious, right? 1975. It was still very, very expensive. And let us consider for simplicity a closed shell and let the Hartree-Fock wave function, this is later determinant, be the one determined Hartree-Fock wave function where xi indicates all the spatial and spin coordinates of the electron I. So this is just electronic coordinates, no wave function. And then they go on and describe the basics, and then they don't really go into detail, and it's a very laborious derivation. And yeah, let's not go into details. I'll save you from all of these details. It's a already quite long lecture. But let's go back to the LYP paper. They basically, all they do is translate this formula, which was useful for a short amount of time because it just approximates MP2, which is already not that good, into a density functional. Just the density dependent contribution. Conservative is at 846. So they also gained some from their 740. They get 100 citations. Good for them. Not quite as many as the Becke, as the LYP paper. So I don't want to focus on the derivation. This is lengthy but not very instructive in my opinion. But let's focus on the results. I'll give you the formula here. So this is the original formula of Colle and Salvetti. It depends on the Hartree-Fock density. The second derivative of the Hartree-Fock density. There's orbitals in there. And down here you have this density dependent formula, right? Here and here. And then again, they have a table where there's species, closed shell species, experimental correlation energies are known for some of them. You have this original formula, and I visualized these for you. I just copy pasted this into the AI of my choice and asked it to make a plot of it with Python. Again, absolute and relative errors. If you take a look, remember, this is just the smallest contribution. We have here errors, original Colli-Salvetti formula. It's not an exact formula, but the relative error, so the zero line here is experimental relationship. Is throughout krypton and xenon because there's no experimental value. But you deviate, LYP deviates by a maximum of 10% from the exact. Okay, Chris has to leave. Yeah, see you on YouTube. It deviates by just 10%, by less than 10% for all of these systems. There's some small molecules in there, some atoms. And this is on the same ballpark kind of as the original Colle-Salvetti formula. So they did a good job recasting this. And let me summarize. So again, very similar to Becke's thing. They start from a wave function based formula for the correlation energy. They recast the equations into density dependent approximations. So they didn't invent something entirely new. They just cleverly recast it. They took the correct asymptotics and constraints from Colle-Salvetti. The parameters in there are also taken over from LYP, and they have a match. And together with B88 exchange, we have our almost magical exchange correlation function. So how good is it? Now I can finally show you how good is it. And for this, we are gonna take a look back at the GMTKN55. So remember, Hartree Fock 25 all the way up there. LDA 17, MP26. BLIP, if you run it just as BLIP, you get 21.1. Okay. How can this be worse than LDA? Anyone got an idea? It has to do with the little remark I gave you about those functional and what is actually shown here.
It's missing dispersion then, I guess.
Yeah, exactly. So if you run B3, blip D3, it ends up here. And this is less than 10. So this is 9.5. The issue is that because you have lots of non-covalent interactions in this database, and actually it has been criticized for being too focused on non-covalent interactions, you're getting these systems wrong. And LDA underestimates exchange, so you have always like 10% self-interaction error, very roughly spoken. And you can see this as a systematic overbinding. So everything is bound too strongly. That means all interactions are overestimated. And if you lack dispersion, which is always binding, then you get error cancellation or error compensation between the lack of dispersion and the general overbinding tendency of LDAs. And if you remove this, B88 has actually quite a steep enhancement factor, as you just saw. So it's one of the highest curves. It's furthest away from the LDA. You lose this error compensation, and it looks like it's worse, but it's not. It's just a loss of error compensation. This is another important lesson if you think about these functionals and about how good they are. If you really want to improve it, you have to make sure that you compare apples with apples and that your benchmark set reflects that. You should not compare blip without dispersion against something like the LDA. If you add the dispersion to LDA, it gets worse. And this is exactly the last lesson of this lecture. I want to go a bit into detail. This is the kind of type of slides which we'll now always look at for our new ingredients. We'll do the same for hybrid functionals, for the dispersion correction. We take this GMTKN55, but we don't average over everything, but we will take a look at each subset of this large benchmark. So here's the result you just saw in the table, but then there's non-covalent interactions. There's intermolecular ones between two molecules, two benzene dimer, for example, but also intramolecular ones. And these are conformational energies. Like how does the tail of, I'll answer this in a second. How does the tail of a alkyl chain interact with the remaining part of the molecule? It's also non-covalent, but it's intramolecular. Then we have barriers. What's in here is transition states, basically. Isomerizations and large systems, and basic quantities, atomization energies, and small systems. And if you compare BLIP and BLIP with the dispersion correction, you see that these systems back here are all much better, like really a lot better. Barriers, there's not a big change, a little bit worse. Large systems, huge improvement with the dispersion correction. And for small systems, not so much. And it doesn't really matter which type of dispersion correction you use. You can use the Grimme dispersion correction here. D4 is maybe a bit better, but usually it doesn't matter so much. So the more important question is if you use one or not. You can also use the Joe-Trevler or the exchange dipole model of Becke, which we mentioned earlier. So all of these give you roughly the same result. The differences are much small between them are much, much smaller than the difference of having it or not having it, right? So again, BLIP is very good if you include a dispersion correction because of this huge systematic problem. If you just look at small systems, what people did in the early days, where they didn't have the computational resources to run large systems, it's not such a big difference. But so yeah, I've already said that. But let's look at some other functionals to understand this error compensation a bit better. So for example, what about PBE? PBE, without the dispersion correction, looks surprisingly good, right? So we have half the error here, but then it improves, but it doesn't improve nearly as much, right? So PBED3 is actually overall not that much worse, but it's worse for the non-covalent interaction systems, albeit it's much better without the dispersion correction. What's going on there? Wouldn't you expect something which is already good, much better than BLIP, to improve even further if we had this correction? I would.
Is that because of the wrong way S works for longer
Yeah,
ranges
you're
and
on
stuff?
you're on the right track. Um, so
Because I just wanted to ask that question on which of these parts of the benchmark this the way that PBE treats the S wrongly
I'll have the curves for you in a
affects it
second, okay?
most. Okay.
Du hast den Braten gerochen. But um, so yeah, for a small system, no, not so big of a difference. Barriers are maybe a bit worse, but look, PPE and BLIP are already quite similar. There's let's look at something which has an even larger difference, like ref PPE. Ref PPE is even more towards BLIP, right? So this is much more similar. You see the numbers are almost the same. There's quite a big improvement, by the way. All the best the best ones in each column are fat. Bit bad worse here, but it improves again a lot if we include the dispersion curve. Actually, this is very good value here. Same same as here. Ref PPE gives you the best non-covalent interactions, coming from almost the worst, coming from the worst, not almost. And it's actually one of the best GGA functionals on the whole GMTKN55. Now let's look in the other direction. This is, I think, the last one I want to look at. PW91 is again very similar to PBE here. We have the best numbers without the dispersion correction. And from what we have already discussed, you might guess that this is because PW91 is very LDA-like. Error compensation leads to this working well with all the dispersion correction, but then if you add the dispersion correction, it doesn't help as much. So I had the same plot here, but then I was kind of annoyed that I cannot have just the ones that I showed you here. So I sent this picture to Gemini, or I guess most other AIs would work. I need the curves. I need just these curves. And I thought, well, it will do some image processing and grab out the curves and make them into a nice plot. No, what it did is actually it created a Python script which has the analytical enhancement factors, which it looked up from the original papers and allowed me to print them now. So now we have a nice plot. And actually, after that, I had a discussion with it about these papers, about the stuff I'm presenting to you today, and I was blown away how good it is. So what I want why I'm telling you this is if you want deeper insights into this after the lecture or when you watch this lecture on YouTube, please cite these papers, do a screen cap, shoot it over to Gemini or the LLM of your choice, and ask it about it. I was just blown away at how deep this thing knows density functional theory, and how immediately it understood what I wanted from it, without much context. So you see, this is the context I gave it, like 15 words and a bad low resolution picture. Very interesting, very powerful to learn more. So here's the plot, and this is, I think, what you, Niels, mentioned. So PW91, you see it comes down again here at large distances, at large values of S, which are also a large distance away from the molecule. So this guy is very much LDA-like, it comes back to the LDA back here. That means this thing is overbinding a lot. And then because it overbinds a lot, this binding is not the same binding you would get from a properly behaved dispersion correction. So the dispersion correction cannot repair this because the dispersion correction is only an attractive force. If someone thinks overly attractive, but with a wrong asymptotic behavior, you have no chance to repair it with a dispersion correction. Therefore, functionals which do not have this overly attractive nature, but have a steep enhancement factor like B88 or REF-PBE. By the way, you see that REF-PBE behaves different, right? If you remember the Becke paper, the one thing he had before, like not the first one, but the second equation he had, was a bit more like this. It has the saturation, and he explicitly mentioned tuning it to get this increase to fulfill one of these criteria. The criteria that he fulfilled is specific to molecules. So B88 works particularly well for molecules, but if you are in a solid, you don't have this decay towards infinity because there's other things coming. And therefore, B88 has never been prominent in the periodic and in the solid state community, where functionals that have this more or less the saturation here are better usually. PBE sol, especially because it kind of includes dispersion. PBE sol, actually, I don't have it here because I couldn't ever find data for the GMTKN55, is probably the most LDA-like, so it will be pretty good, reasonable looking without the dispersion correction, but it won't be any good with the dispersion correction. And this is a trend which can be generalized. So these functionals should behave basically like REF-PBE. If you just go to the GGA level, that means you have a high enhancement factor, you don't have this overbinding, but you add the correct dispersion with the correct R to the power of 6 range dependency back in, and then you have something which works very well for non-covalent interactions and also for basic and small systems. The barriers are bad for all of these, right? You see this here, the dispersion correction often makes it worse, but this has nothing to do with the dispersion correction. Again, this is error compensation that this here looks good. A real hybrid functional, which you need to remove the self-interaction error, gets to much lower values here, even better, much better than this. And this is a fundamental shortcoming of GGAs, that barriers are systematically underestimated. And this is exchange related. This is not evident from comparing equilibrium structures. You need transition states in your benchmark set to notice this. And the first way we'll see how to fix this is by adding non-local Hartree-Fock exchange and hybrid functionals, topic in the next lecture. The other thing which I discussed is that these semi-local functionals work quite well for small molecules, but they lack this dispersion, which is a problem in solids. In large systems, the more, like a protein has lots of dispersion interaction because it's between all the molecules, even at the large distance, and not just between bound molecules. So this is overlooked if you only look at small systems, but you can see it And the best way to do it is not to have an overbinding functional which seemingly fixes that, but to fix this with a proper dispersion correction. This is why you always should use the dispersion correction. Density functionals have a very hard time of getting the correct asymptotics for dispersion just from the density, for reasons we will discuss in the lecture after the next lecture, I think. So something else I wanted to point out is that I hope I could convince you or show you today that functional design is not really a science like solving an equation. It's more like it's as much art as science. So you have to find clever ways to recast the equations, to identify very suitable wave function dependent stuff, which you can then recast into a density functional and combine these ingredients in a mathematically clever and practical formalism that this gives you the correct shape of the enhancement factor. And we saw already an onset in Becke's paper where he fitted this parameter to reproduce exchange correlation energies or exchange energies of rare gas atoms world. We will see much more of that going well beyond atoms, where some people have hundreds of parameters or 40 parameters in their functionals, and they just fit them to reproduce huge experimental data sets. Then you have other approaches which are more like the PBE family, which focus on something else we saw today, these fundamental constraints, the correct evolution of the enhancement factor at large distances, the correct behavior of the exchange hole, and such things. And this is another kind of family and functionals, and I think this is the topic of the lecture number 7. You can just take a look at the thing I showed you in the very beginning. And with this, I think we are at the end of this lecture. Bit over time, if I'm not mistaken, but I hope you could bear the extra 15 minutes. In the next lecture, as already mentioned, we'll talk about the adiabatic connection, which is the concept underlying the combination of hybrid function, the combination of density functional theory and Hartree-Fock. Again, we will use Becke's work as the starting point, but also see how other people arrived there. And in the lecture afterwards, we will discuss how we can fix or repair DFT by adding dispersion corrections. Before I stop here, are there any more questions? Niels, did the final part answer your question?
Yes, I think to the most extent. One question that popped up was then that, I mean, the S values for all these different functionals, surely they look all different in the realm where S is fairly large. When you go back
Mm-hmm.
to the graph, like starting from any value really above 2 or so. Is
They
the
start to
reason for
diverge,
why
right?
diverge, yeah, between the different classes, like your
Mm-hmm.
B88 PBE versus PW91. And
Mm-hmm.
is the reason why usually only one kind of exchange functional is paired up with another correlation functional behind that to sort of compensate for these different behaviors in the end? Because I mean, they would give different energies in the, well, they obviously do give different energies as you have outlined multiple
Yeah.
times, but do you want them to be close to each other, or do you
So
not, for a given
let
system
me
that's
let me
being
answer the easy
periodic?
part
Or
first.
yeah.
The absolute energy that you get from a functional, if you meant that, not the chemical energy, but the absolute energy is not has no meaning. Only within a certain functional, you have this variational principle where the better your wave function, the better your SCF solution, the lower the energy. But you cannot compare the total Hartree-Fock and the total energy from a from a BLIP calculation to a PBE calculation.
No,
These
no, no,
numbers
that's
are
not what I meant. That's not what I
as
meant. When uh, during the development cycle of a functional, where you then compare it to
you
energies
mean the
obtained
chemical
from
energies
the chemical
in
energies
on the
obtained
benchmark
from
set. Yeah.
atomizations, yada, yada, yada,
Mhm.
where B88 was developed, and then at some point a B-lip came into existence, but not
Mhm.
a BPBE, where I don't know
Yeah.
where Becke has worked with
So
Purdue and all the others to to make that functional. Like,
I haven't found a paper on this, so I'm telling you what I think. It's not
mhm,
founded in anything that is published, but my feeling is that these combinations work or don't work for reasons which are usually quite a bit more complicated, but they go into the same direction of what we discussed on this slide. So it's kind of one of the exchange functionals lacks a bit of exchange in the long
mhm.
range, and then you have a correlation function which overestimates it a bit, and this leads then to some favorable error compensation. And
Yeah, yeah.
there's many of these things which I don't even know if they are fully understood. I'm sure people have their theories, like I have my little pet theory here, but these things probably work well together or don't work well together.
Mhm,
And
mhm.
but
And that
what is
is more or less empirical. Yeah.
yeah, but what is clearly the case is that this exchange part is 10 times more important than the correlation part. So
Sure,
you
sure.
can
But
you
but
can
but in that
probably,
section for these smallish S values, maybe the correlation can uh,
but this is this
take
is the
quite a
LDA
bit of.
like section, right? If you think about a molecule where you usually a small molecule, you have a lot of high S area relative to the low S area because the
Mhm,
density
mhm.
is fairly this S is fairly large if you go away from the nuclei. So you
Yeah,
have a lot of surface in a small molecule relative to the volume compared to a large molecule where you have a lot of volume and only a
yeah.
little surface, right? This is v to the power of 3, v to the power of 2
Mhm,
ratio.
mhm, mhm.
Even the size of animals depends on that, depending on the environmental temperature,
Yeah.
right? So if you have that, it means your functionals are sometimes better for these functionals differ not so much for small molecules. You see this here also in the data, right? They all give
Yeah.
fairly similar errors in small molecules, but when you go to to big molecules, this becomes important and starts to matter.
Oh, yeah,
But
yeah, yeah.
maybe it's also just that these small molecules, the energies are smaller, right? So this is another topic we will discuss in the lecture about benchmarking. If you compare the chemical reaction energy of two very large systems, it can be a very large energy just because you have three or four bonds forming.
That's why they always compare absolute and relative errors. Yeah.
Exactly. But relative errors are also sometimes difficult because now assume you have two an NCI system where you have a weak interaction, just zero point 0.5 kcal per mole, and
Mhm.
your one functional is off by 0.5 kcal per mole. So it's 100% error, but still it's just half a kcal. So is it that important for two large systems? Some chemical reactions are with a reaction energy of almost zero. So if you then look at relative errors, then you get huge relative errors,
I'm with you. Yeah.
but the absolute error is very small. So relative does not solve the problem. You need to look at absolute and relative, and for absolute, you have the additional problem that the size matters.
Mhm, mhm.
So we will discuss how this is solved. This is why we are not looking at just an MAD, but at this weighted MAD2, which uses some clever statistics to re-weight the impact of these factors on every set. You cannot just compare everything relatively or absolutely, is what I'm trying to say. So
Okay.
it's not straightforward usually in chemistry to compare these numbers. There's good reasons for both. But in this case, I'm pretty sure to come back to that. Uh, my initial assumption was wrong, and the smaller errors here are more because these systems are small and more similar.
Mhm. All right. Thanks.
All right, Brock, any questions?
Yeah. So one of the things that you mentioned is that like dispersion corrections become kind of problematic with certain functionals because
Mhm.
they're not designed for the dispersion, right? They're not uh, B88 existed before D3. Um,
Yes.
so one of the things that I think is an interesting note is like I know that there exist functionals which are made specifically be like for non-local corrections, dispersion
Hmm.
corrections. So
Hmm.
what kind of an obscure functional, but the C09 exchange, that functional was developed specifically to work with the van der Waals density functional
Yeah.
of
There's a
Lundqvist
B88
and
opt, I
Landgraf.
think. There's like a specifically adapted version of B88 to work with the non-local DF van der Waals. But
Hmm.
so yeah, I think there's even a PBE variant of that. You're right. What's the
Uh,
question?
the question is like, is it worth designing a functional that fits with your like how important is it really in the sense of, I'm running, let's say I'm running 10,000 calculations on molecules or such. How critical is it that I really match my dispersion exactly? Like, is this a problem that manifests in every calculation, or is this
Yes, this
sometimes
is a problem.
isolated?
The imperfection in these functional matters, the main problem is that depending on this over-under binding aspect, functionals, the dispersion is a long-range correlation effect, right?
Hmm.
What these functionals recover with their exchange with their correlation functional is the short-range dispersion effect.
Hmm.
The part where it matters is this mid-range regime. Between the long range and the short range, you have a mid range, and this is where kind of you have interference between the functional part and the dispersion correction part, or the density part and the dispersion correction part. And to match these together, people invented damping functions. Because this is
Hmm.
exactly what this damping function does. It shifts the onset and the offset and the steepness of this intermediate part of the dispersion correction, because this is something you can adapt to that part of the functional. And now you have certain functionals which do that very well, which have a very clear cutout, and you have functionals which poorly do that, which
Hmm.
recover some, mimic some dispersion like PBE sol, and that dispersion correction won't work that well. Actually, one of the functionals, like the best case you want to have from the perspective of a dispersion correction, is that a functional that does a good job at the short range correlation, does a reasonable job or a good job at the mid range correlation, and then sharply cuts out. Because this mid range part has still some non linearities, complications, which you cannot mimic by a force field term, which most dispersion corrections turn out to be in the end. Like even the
Hmm.
VV10, for example, which you have on the Omega B97 family, it behaves very, very similar to D4 or D3, which is in the end a force field term, right?
Hmm.
Sometimes
Hmm.
with a free body, sometimes without. But in the end, they are more similar than they are different. This is what I mentioned before on this slide. And you can match these force field terms, and these force field terms are very good at doing this long range stuff where things are far apart and it's really 1 over the r 1 over r to the power of 6 and not some weird density overlap stuff. And a function that does very well at this is, for example, R2 scan 3C.
Hmm.
You clearly see this in problems where mid-range dispersion is important. I think I even have a slide on this. Yeah. This is the interesting example. It's in German. Sorry, I did not translate it like you suggested. Now I and then this shows the dispersion energy or the experimental energy here, absorption energy of benzene on gold, silver, and copper, and then you
Hmm.
have CO and MgO and CH2 C2H2 on natrium chloride, sodium chloride. Now
Hmm.
I'm getting lost in translation too. And you see here how different dispersion corrections with different functionals work for this. Like, so what you want to have is like this pattern reproduced here, right? And
Hmm.
I color coded this. This is from the R2 Scan 3C paper. DFT part, this is the functional alone.
Hmm.
This part is the dispersion correction. This is not possible to decode and scan RVV because it couldn't get the contribution separately.
Hmm.
And then you have some GCP in case of R2 scan 3C. This is a composite method, right? And you have a spin
Hmm.
orbit effect, which I calculated for all of them. And now if you start back here with BLIP D4, BLIP is a functional which cuts out very quickly. There's no mid-range dispersion, so it's actually repulsive. You see this here, right? There's no attraction whatsoever between benzene in the equilibrium geometry and the surfaces. And the dispersion correction needs to do all this interaction, even the mid-range part, and it's not so good at that, right? So therefore, dispersion in the end is overestimated for this because they are made for molecules. If you would calibrate it for the system specifically, it would be better. But here, the dispersion correction just has to do too much. And the result is qualitatively okay, but it's not quantitative. With M06 to LD4, it's very difficult because here, depending on what metal you have, you get wildly different contributions. The dispersion correction has no chance to repair that, right? You cannot do a repulsive dispersion correction. PBE is a bit better here. PBE recovers part of this mid-range dispersion already, mid-range correlation, but it's only a little bit better than PBE, right? It at least binds the systems, but you see, this is what I mean with over versus under binding, right? So this is a bit more binding. And then you have these functionals here, all scan functionals, R2 scan eventually, which have this meta GGA part. They also include the curvature, and the curvature now gives additional information about this mid-range correlation part. Because what you have here is a system that sits at the interface between periodic solids and molecular systems. What we just discussed before. You cannot use either for them. You could for a gold slab, big gold period. PBE solid is perhaps very good, but you have a molecule on top of such a periodic system here. And R2 scan, because it uses this information from the curvature to switch between the two regimes, does a very good job here. And it does a quite nice job at this mid-range part. So it does bind all these systems. And then you see that the dispersion correction, I think it's D4 in this case, only has to do a small part. And this, it does well because this long-range correction between the benzene and the layers of gold, this third and fourth and fifth layer of gold atoms, therefore it works fantastically well. What it just can't do is the interaction in the short range between the benzene and the first and the second layer of gold. This is the failure you see here. Hisakro, did this also answer your question regarding underbinding, overbinding? Great. So he answered yes for the YouTubers watching us in the future. Nice. So you ask, what if the system is not periodic? So a single gold atom is a molecule. It's very different from a periodic gold slab. And you kind of have a continuous transition from a single gold atom to ever larger gold clusters to an infinite gold. It basically, you can see how the performance of different functionals varies across this. It's an interesting test. Play around with it and learn something from it. Okay. This is much more than I wanted to say in this lecture. We already covered half of the dispersion lecture now. And since it's getting late, I think it's a good time to call this a day. I'm happy to discuss this with you further on afterwards, but I will make a clear cut now for the recording and say bye-bye and thank you for listening. And I hope to see you again at the next lecture, number 5, about hybrid functionals and the adiabatic connection. Okay, now we can make a cut. Hisako, sorry, I mispronounced it every single time, I guess. You ask, what if this, do you think the trend will be the same? Yes, I do think the trend, if you go from a gold atom to a gold slab or periodic gold, R2 scan will be superior. R2 scan is really, in my opinion, is just the first GGA functional, the first fundamental from constraints derived, not empirically fitted meta GGA functional, which really had some new physics in there. So which meant to differentiate between being in a solid and in a molecule. There's other functionals. I don't want to make a commercial for R2Scan 3C or R2Scan here. For example, also M06L, I think, is surprisingly good at predicting barriers without any Fock exchange, which is something which you typically only get from hybrid functionals. And there's another one from the Martin Head Gordon group. They are doing like a limited empiricism approach. It's called B97MV. And this is even better and a bit more robust than the M06 functional. It's also quite a couple of years younger. And they managed to create a functional with 14 parameters or so compared to the 40 of M06L, which also does a surprisingly good job at deciding between this. It's just that they did not design it fundamentally, but they fitted it to a large number of data.